Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture 55 of the course Theory of Computation. In this lecture, we see yet another NP-complete problem, which is knapsack. Right? In the previous lectures, we saw many other NP-complete problems. So we saw problems which are based on Boolean formula like SAT, 3SAT, etc. We saw problems which are based on graphs, clique, independent set, vertex cover, etc. We saw subset sum in the previous lecture, which was asking, given a set of numbers and a target sum, is there a subset of that set which sums to the target sum? Right? So all of these problems are NP-complete. And just to remind ourselves, NP-complete problems are considered to be the hardest problems in the class NP, and it's widely believed that they do not have a polynomial time algorithm, right? Because if we show that any NP-complete problem has a polynomial time algorithm, we would be proving that P equal to NP, which has been a big open question that has been open for 50 years, right? So it's widely expected or widely believed that P is not equal to NP, and hence nobody or most people don't think that we will be able to provide polynomial time algorithms for these NP-complete problems, right? So this lecture, it's going to be a brief lecture. We are going to see another problem called knapsack. As we will see, there is so we'll see the problem first. So there are n objects, right? So they're indexed 1, 2, 3 up to n, and 1, 2, 3 up to n. Each object has a weight w1 to wn. So first object has weight w1, second has the weight w2, and so on. And each object has a value v1, v2 up to vn, right? So there is a weight and a value. So something like gold will be very valuable for a small weight, but something like iron would be not so valuable for the same weight, right? So the setting is this, that you are a thief or a robber, and you are robbing some place where you have a lot of assorted collection of objects, and you have brought a sack with yourself, or that's what the knapsack indicates. You have a sack or a bag with yourselves which can carry objects, right? But that has limited capacity. There is only so much of items that you can put into your sack. So as a thief or a robber, you want to maximize the value of the items that you carry, right? Only then can you sell them for maximum money, for all the risk that the thief is taking. So he wants some payoff, right? So he wants to maximize the value. However, the bag is kind of old or torn or whatever. And any bag has a physical capacity, right? It will not be able to hold more than a certain capacity. So it cannot hold items which are weight more than something. So the goal of the thief should be to pack as much items as possible such that the weight does not exceed the weight capacity, and we want to maximize the value of the items in the bag, right? So this is the requirement. So now we'll formulate this question as a decision problem. So there are n items 1 to n, index 1 to n. They each have a weight w1 to wn, and each have a value v1 to vn. Now given the capacity of the bag w, like capital W, and given a goal value g, right? So g means it's the goal that we are given. So we have to the robber has to bring at least g worth of items, right? But his bag can only carry w kilogram of items. So the question is, does there exist a subset of items whose sum of weights is below the capacity, right? That's what is indicated here. Sum of the weights is below the capacity, whereas the sum of the values is exceeding the goal that we have. So this is a natural thing that one would want to do. One would want to get items whose weights are below capacity, but the value is above the goal that we have, right? So this is at most capacity W and value is at least the goal, right? So that is the question, and this happens to be NP complete. So you may feel that this is like, even in subset sum we wanted to pick a subset of items or subset of numbers which sum to it, which gave the sum to a target. Here it is similar. Here also we want a subset of items that satisfies this as well as this, right? So in fact this problem also is NP complete. First of all, it's in NP by the same standard guess and verify approach. So we can guess a subset, we can not deterministically pick or not pick each element, and we get a subset, and then we just verify the subset, verify if the subset satisfies these two constraints, the sum of weights being at most the capacity and sum of values being at least the goal. So if it is a yes instance of knapsack, then one of these guesses will be correct. And then to show the NP completeness proof, we have to show that some NP complete language reduces to this problem. So we will reduce subset sum to this problem, which is not surprising because subset sum seems similar in flavor, right? So in subset sum also we had to choose a subset of items, right? Subset of numbers, and then it had to satisfy certain property. Here also we had to pick a subset of some items, right? So both are similar in flavor, right? This is also something that is usually a theme. When you want to show that a certain language is NP complete, we try to look for problems that are similar to this, that are known to be NP complete. Usually these problems turn out to be easy to get a reduction from, right? So since subset sum is similar in some sense, we are going to reduce from subset sum. So what is subset sum? Given a set S, let's say S1 to Sk, like k numbers, and a target sum T, we wanted to know whether there is a subset of this set, capital S, whose elements sum to the target sum, right? Is there a subset of capital S, such that the elements of that subset sum to T, right? So given this, we will construct a knapsack instance, right? So knapsack, we need n items where the sum and with weights and values specified, such that the sum of the weight should be at most something, sum of the value should be at most something. So to completely specify the subset sum, knapsack instance, we need to tell what are the n items, what are each of their weights, what are each of their values, what is the target or what is the weight capacity, and what is the value goal. So these 5 things need to be, or these 4 things, W1 to Wn, V1 to Vn, W and G, capital W and capital G need to be specified to provide the knapsack instance. So let us see what is the knapsack instance going to be. So we have k items, so where k is the same as this k, right, this k. We have k items and the weights are going to be S1 to Sk, right. So the whatever the numbers were in the subset sum instance, the weights are going to be the same, S1 to Sk. The values are also going to be the same, right, and the capacity is going to be T, which is the target sum, right. Capacity is going to be T and the value goal is also going to be T, right. So it's a very simple reduction. So given the subset sum instance, we repeat the numbers as the values and the weights, and the target sum is repeated as the weight capacity as well as the value goal. So both of them, it is the same instance repeating. So virtually it takes just the time to write this down. There is no calculations needed, right. So given the subset sum instance, we can almost immediately write down the knapsack instance. Hence this is so I am not bothering to explain much. This is a linear time reduction, which is also polynomial time reduction, right. Now it's even the correspondence is fairly straightforward. So if this knapsack instance is a yes instance, so now we have to show that the subset sum instance that is given here is a yes instance if and only if this knapsack is a yes instance of the knapsack, right. So for a yes instance of knapsack, what we have to satisfy? We have to check whether there is a subset, right, meaning a set I with indices, which is a subset of indices such that the sum of weights is at most the weight capacity. So the weight capacity here is T. The sum of weights is actually sum of SI that belong to I. So is there a subset of the elements, or is there a subset of the indices such that for these indices the sum of SI is at most T. So the weight capacity gives us this, and the value capacity, or the value goal is G. So the value goal is G, which is also T, right, which is T here, but the values, individual values, are S1 to Sk. So if you sum the selected items, right, so the selected items, which is the set I, the sum of the values should be at least the goal, which is T. So sum of the values should be at least T. But what are the sum of the values? The values are actually S1 to Sk. So that gives us that summation Si of the selected items should be at least T. So now we have two inequalities. One of them says sum of the Si should be at most T, and the other one says sum of the Si should be at least T. So combining, so if the knapsack instance is a yes instance, both of these must be satisfied. So combining this, if the knapsack instance is a yes instance, we have this, which is that summation of the selected items, or summation of the selected Si is equal to T, right. So a yes instance of knapsack, we have this, but this is exactly what happens in the yes instance of a subset sum, right. This is a subset of the given set S, right. It's a subset of the given set S which sums to the target sum, right. So now it's very clear that a yes instance of a knapsack gives a yes instance of the subset sum, and the yes instance of the subset sum also gives a yes instance of a knapsack, right. So the reverse direction is also easy. It's pretty much the same argument in the opposite direction, right. So this means that the correspondence is also proved. A yes instance of knapsack implies a yes instance of subset sum, and the other direction is also the same. So this shows that we have a yes instance of the knapsack if and only if we have a yes instance of the subset sum, and together this implies that the knapsack problem is NP complete, and that's it. It's a rather brief proof, but that's all there is to it, right. So knapsack, where there is a problem with weights, values, etc. Now we reduce subset sum to this by making the weights and values equal to the numbers in the subset sum, and the weight capacity and value goal both equal to the target sum in the subset sum. That gives us that if the knapsack is a yes instance, that gives us a subset whose sum is equal to the target sum, right. If there is a subset with the target sum, the same subset will satisfy will be yes instance of the knapsack also, right. It's fairly straightforward. So that shows that, and it takes polynomial time to write down this instance. That shows that subset sum reduces to knapsack, right, and that completes the proof. Hence subset sum is knapsack is NP complete. Now one small thing I want to mention. So there are two parts in showing that NP completeness, right. So there are two parts in showing NP completeness, right. So you want to show NP completeness, let's say NP completeness of, let's say, C, we need to show two things. One is that C is in NP. Two is that for all A in NP, A reduces to C in polynomial time, right. And the second condition, right, this condition can be actually this can be replaced by B reduces to C in polynomial time where B is an NP complete problem. So instead of showing that all the A in NP reduces to C, we just show that a selected NP complete problem reduces to C. In fact, that's the strategy that this is already something that we have already seen. So here we reduced subset sum, which is already shown to be NP complete, to knapsack, right? So now this part, the part 2 alone is usually referred to as NP hard, or NP hardness. So to show NP completeness, we need to show that C is in NP, which is condition 1, and second is to show that C is NP hard. NP hard means all languages in NP reduced to C. Equivalently, some NP complete language reduces to C, right? So sometimes the second condition is referred to as the NP hardness, right? So I just wanted to stress on this. So some place where so NP hard is usually used in a way similar to or synonymous with NP complete, because usually the first thing is usually easy to show that something is in NP. So the to show something is NP complete usually boils down to the proof of NP hardness, because the part 1 is easy, part 2 is the one that is the challenging one. So, but there are languages which are not in NP but are NP hard, because you could be something even more harder than NP, but all languages in NP can be reduced to this. So being NP hard does not imply that the language is in NP, right? Anyway, my point was to highlight this terminology, because as students of a theory of computation course, or when we are learning computational complexity, you may come across this term called NP hardness. So NP hardness usually means this, that all languages in NP reduce to that language, right? And so to show something is NP complete, we need to show the membership in NP, which is condition 1, and to show that this language is NP hard, which is condition 2. So these two together show that a language is NP complete, right? So that's it as far as lecture number 55 is concerned. So we defined the knapsack problem, which is a decision problem, and we showed that it is NP complete by reducing it from subset sum, and we had a brief discussion on NP hardness. And that completes lecture 55. In the next lecture, lecture 56, we will see yet another NP complete problem. So see you in lecture 56. Thank you.